Hi, I'm Thomas Flynn, and thanks for coming to my virtual talk on bounding the expected runtime of nonconvex optimization with early stopping. This is joint work with Kwangmin Yu, Abid Malik, Nicholas D'Imperio, and Shinjae Yu. And we're from the Computational Science Initiative at Brookhaven National Laboratory. So to set the stage, imagine that you're developing a self-driving car. You'd want this car to be able to understand all the different imaging that it's receiving, such as if there's people in the way, understand if there's stop signs, things like that, because you don't want to have any lawsuits. So in 2020, the way that you would do this is you'd have a model that takes as input these images and will tell you what they mean, right? It's a green light, or it's a yield sign, or it's a stop sign. So to do this, you'll get a data set D of image and label pairs, and you'll have a family of models parameterized by W, and you'll have a loss function F. And using this, you define your empirical error function, which is the error of the model over your training set. And training the model means minimizing this empirical error. The algorithm that you'll use for this is usually some variant of SGD. In SGD, you get a mini batch. B, you compute the gradient over this mini batch, you update the parameter using some step size eta, and you repeat this process. Now, so far, I've just defined an infinite sequence. How do we actually stop this? And once you have a stopping rule, you'll want to know what are the convergence properties. Here, we're focusing on non-convex optimization. So by convergence, we mean the algorithm finds approximate stationary points, which are points where the gradient is less than some user-defined value epsilon. A key technique that people use for analyzing non-convex algorithms is the randomization technique. So in the randomized stochastic gradient algorithm, you start with a maximum running time n, and you choose a running time t between 1 and n. And you run the algorithm for this random amount of steps, and you return the final result. And there's a by now classic result that you can set up the step sizes in such a way that this RSG algorithm has a convergence rate of 1 over a square root of n. And that's very nice, but the natural question is, what about other stopping rules? Maybe you stop at a fixed time, or maybe you stop based on some sophisticated criteria involving a validation set. This work focuses on the latter situation where you're using a validation set to stop training. So let V be a validation set and define this validation function FV. It's just the average error over this set. SGD with early stopping works as follows. It's just normal SGD, except every m iterations, you're going to check the performance on the validation set. Once the point that you find is an approximate stationary point for the validation function, you stop. So you're going to want to wonder, when is ES-SGD well-defined? And what can you say about the performance of the final iterate that it returns? Now, formally, ES-SGD stops at the time tau, defined as follows. Tau of epsilon is the first iteration number where A, it's a multiple of m because we're only checking the criteria every m iterations, and B, it's an approximate stationary point for the validation function. Now, intuitively, in order to get any kind of guarantee, you'll need to have some relationship between FV and F. Because if FV and F are totally unrelated, there's no reason to think that doing gradient descent on F will generate an approximate stationary point for the validation function. The way that we formalize this is as follows. We assume that the gradient of F has a Lipschitz property with respect to its input. So a small change in the input should lead to a small change in the gradient. And using this property, you can show the following, that the distance between the gradient of the training function and the gradient of the validation function can be bounded in terms of the Wasserstein distance between the training and the validation sets. So this is just some distance between the two probability distributions that G and V define. And in addition to these assumptions, we also have the standard bounded variance assumptions, and also an assumption on the Lipschitz property of the gradient with respect to the parameter W. So using these assumptions, the questions that we ask formally are, first, how many gradient evaluations does SVRG need before it terminates? And then, how good will that final point be that it returns? Right? Because the final point, you're interested in how good is that as an approximate stationary point for the training function when your criteria is in terms of the validation function. To formalize this, we use the notion of an incremental first-order oracle. So IFO of epsilon is how many gradient evaluations occur when you run the algorithm for tau of epsilon steps, right? And what we show is that for all epsilon above a certain threshold that depends on the distance between the training and the validation sets, first, the expected running time is finite, and you can bound the gradient evaluations as follows. Essentially, this convergence rate is 1 over epsilon squared, where epsilon is the user-defined bound on the gradient that they want to achieve. And not only is the expected time bounded, but the quality of the final iterate in terms of the training function can be bounded in terms of that threshold epsilon and the distance between the training and the validation sets. And the proof analysis essentially starts from the analysis of the randomized stochastic gradient algorithm. And then we use the optional sampling theorem to extend this to go beyond just using random and independent times to the broader class of stopping rules that can depend on the trajectory. So the SGD with early stopping is only one piece of our analysis. We also look at other algorithms such as decentralized SGD. And we also formulate this in a much more general noise setting where you can have a combination of contracting and expanding dynamics. And beyond that, we also look at what is the stationarity gap of the testing distribution, given that the training and the validation sets are generated using samples from this testing distribution. So thanks a lot for your attention.